Okay, the next big subset or area of encryption I call public/private key infrastructure, PKI. It's been around for a long time. You can go read the chapter, read up on how long it's been around. But the idea is, instead of using a symmetric key or the same key for encryption and decryption, is we will use different keys for encryption and decryption. The analogy I like to use here is, those lock boxes that they have for a lot of mailboxes nowadays, where the postal worker can open your box with. They have, I guess we'll call that a public key. They can put whatever they want in your box, and you have the private key. You're the only one that can get things out of that. So we have these two keys, a public key and a private key. Anyone that we want to communicate with us, we will send them, or they will somehow get a hold of our public key. They will encrypt with that public key, and then we will use our private key for decryption. So once again, the main facet of this is the public key is publicly available to anyone. And how do they do that? Well, these keys are mathematically related somehow. There's various algorithms to achieve public key encryption beyond the scope of this class, but they are mathematically related keys, and as they're funneled through this algorithm, the algorithm will then decide if or calculate or compute the appropriate decryption. One problem that solves is I don't need to worry anymore about key exchange. Public key, anyone can have it. I don't care. Give it to anyone because they can encrypt it. All they can do is encrypt messages with that. And since I'm the only one that has the corresponding private key, I'm the only one that can decrypt. So it makes it a lot safer. Private keys are never distributed. We keep them secret, safe. Other things. We can ensure confidentiality when we're sending messages. When receiving messages, we can ensure authentication or data integrity, make sure it actually it hasn't been changed en route. Anyway, there's a lot more information about that. We'll look at an example in a second. I guess we can look at, for a minute, let's look at SSH as an example. So I don't care. We already know what SSH does, but one of the first things it does, SSH makes use of public and private keys. So actually uses Diffie-Hellman protocol for exchanging keys if necessary. But you can see there's other things about, what kind of key should I look for? Maybe, load these. I found some keys here in this file. It talks about different algorithms. You'll see some stuff like SHA-15, SHA, AES, all these ciphers anyway, a lot of stuff about encryption. There's a ton here that I don't know the half of. But the most common encryption and decryption, PKI with SSH, if you look in our .ssh directory, you'll have a public key and a private key. So my public key looks something like this. Anyone can have that, right? And as an example, I could go stick this for SSH. How it works, I could go stick this public key on a remote server. And then when I try to SSH to that remote server, it will, if I want to do passwordless authentication, it will automatically encrypt my data stream with this public key without prompting me for a password. My corresponding private key is just something longer. And anyway, RSA is an algorithm, Rivest, Shamir, Adelman, or something like that is what it stands for, the authors of this encryption algorithm. DSA is another encryption algorithm. And so we don't need to get in much detail there. You can read in your book about anything that's relevant. I don't think they talk much about any of this. But one thing that I will point out is You can go read about block ciphers versus stream ciphers. A block cipher is where we take a block of bits at a time and we encrypt them. A stream cipher is where we take a stream of bits. As the bits go streaming past, we'll encrypt them on the fly. That's a very high-level overview, and it's a terrible explanation of how it works. But in general, that's kind of how it follows, and you can go read more about that. But what I wanted to get to is key size. So, yeah, public and private keys are great, but once again, if my keys aren't large enough, then it's feasible that a brute force attack would work. That a computer can now try so many different combinations of keys. It can flip through those bits so fast that it could guess my private key. If I chose a very small key size, I want 256 bits, 128-bit. And I don't even know what the state is today of how much they can crack. RSA, I think, uses 1024, but you can tell it uses 2048, and that makes it a lot more secure. But the takeaway I want you to know is the larger the key, the better, in general. One last thing to talk about for encryption. And once again, we're just giving a very high-level overview. You can major in encryption. There's courses in encryption, but a digital signature also kind of follows along with encryption. So, what does a digital signature do? A digital signature actually ensures that the message, or the person who sent the message, really is who they say that they are. So, for example, let's see, 1 second. So, as an example, Bob, for example, creates a message, generates a hash value for the message. Remember what a hash value does? It hash is a one-way hash function. You pipe it through some algorithm like MD5 or SHA-1 sum. You get this output, and for the exact same stream of bits, you should always and using the exact same hash algorithm, you should always get the exact same checksum or hash code, however you want to say. But anyway, basically, if I can take that, if I can hash a message and encrypt it with my private key, I can create a digital signature. So it really says, hey, this really did come from this person. So Alice receives the message plus the signature. She can recalculate the hash value for the message, decrypt the signature using Bob's public key, and compares the calculated hash value to the decrypted hash value. And hey, voila, we know that this message really comes from Bob. The message then is safe from alteration, but not necessarily from observation. We need encryption for that, but a digital signature shows us that it hasn't been altered. Checksum. Just think of that, hash. The last thing is a certificate. We use this a lot. How do I make sure that the public key really is from the person or entity that they say they are? A certificate is one way of doing that. And you've used certificates a lot. If I were to go to like Amazon.com, we say HTTPS. S is secure, right? And that means that if my page will load here, that we are using a certificate. Let's look at more information here. So if I look at my certificate, we can see a certificate has the public key in it. It tells us the public key algorithm. It tells us a bunch of stuff about the public key. It has the public key in here. And basically, a certificate is signed by a trusted third party. So we can see here in this one was signed by DigiCert, which interesting, right? They're a local company here in Utah and Lehigh, and have an office here in St. George. But anyway, so it established a certificate establishes the validity of that particular entity, that they really are who they say they are. So there's a quick overview of encryption. Exciting. Go read your book for some more information.